Good morning, and as always, welcome to Rudy's Electronics Lab. A couple of days ago I posted an episode where I basically failed to try to install additional functionality into my CMU device over here, and that is the IQIF unit. And it felt like a dramatic thing. My device was not working properly at all anymore. I even thought that I broke something, and I spent a couple of quite intensive days trying to figure out what was wrong with my unit, and eventually I got it all going now. But I want to share with you what was actually wrong, so also other people might be able to learn from it. And by doing this, I actually also learned a couple of things of this IQ functionality that I think might be relevant for other users that use it, even if they're not installing this card themselves, it's already pre-installed or whatever, because there are some particularities that are not obvious at all about how this card is actually working. So I'll be talking about that in the video as well. Now, I won't be taking you through my whole my whole travels here. Trying to do that would be way too long, so I'm just going to try to highlight the kind of things that were going wrong. Let's start by recapping where I left in the previous episode. Well, at that time the IQ unit was recognized by the system, and the self-tests all were working well related to the unit itself. However, the loop testing was failing, probably because the unit was not calibrating. The intermediate frequency IOs on the back of the device were not working as I expected them to work when I was routing the signal through my device. Even worse, my CMU even refused to start up applications in all type of things, in RF, in particular standards like GSM or WCDMA. It just refused to work altogether. And it started to crash when I was using it, but even when I was starting it up. So it felt pretty dramatic. Now, what exactly has gone wrong? Let me just put it on the table right away. First of all, there were several errors I found out in the Roden and Schwartz documentation about how this unit is supposed to be wired. Secondly, when I was doing this work, I didn't really realize that the card that I bought by eBay was not the so-called CMU B17, which is the card that's supposed to go in this machine, but instead was a CRTU B7 board. Kind of similar but not identical board that is designed to go in another Roden and Schwartz instrument. And finally, I have to admit, I did not go into the version manager and do the so-called firmware update after board change. I should have done that. But I'll get a little bit more into this as well. In trying to get my machine work, I mean, it was quite a quest, a bit of a travel going to different type of things. Where did I base myself on? In the end, on quite a lot of different sources. On the operations and service manual of the device, on the big metal board in the CMU with the wiring diagram. I've been looking around on pictures on the internet, not that easy to find, where I could see the actual wiring inside units of other people, where I could see the configuration on the back panel of devices, etc. I've been looking at the little text that is written on the scrimping on the wires that come with the different units, and it's different for different units. That gives you kind of a clue. I also was looking at the install instruction by the seller and the wiring by the board as it arrived, because my board arrived with the wiring still kind of intact, it seemed, and that also gave me some clues. And I did quite a lot of trial and error here. What are the little red asterisks that you see here on the screen? Well, those are the information sources where at least some errors were appearing in hindsight. Actually, I'm going to talk about each of these 3 points one by one. So let me first focus on the problems that I had with some of the documentation of Roden and Schwartz. And I'm going to talk here now specifically about the documentation on the big metal plate that you have on the top of the unit. You saw it, I think, in the last video, which has a wiring diagram, and exactly the same wiring diagram can also be found in the service manual of the CMU. Now let's go and look at the main issue I had with the Roden and Schwartz documentation. So if you look at this big metal plate with a wiring diagram and also the same wiring diagram in the service manual, you see, and I'm enlarging here it a little bit, you see a particular wire which is called W914. And you read at the bottom of the diagram that the connection of W914 has to be made when B17 is installed, which is what I was doing. Now, what is the thing here? This is wrong, apparently. You really should not connect wire 914 to the new unit there. This wire actually has to stay where it was. It went somewhere else in the machine. I don't know how this got into the manual, but I really believe it to be plainly wrong. Don't touch connector X517 on the board. In the grand scheme of things, where is this particular cable? What does it do? Well, on the left of the panel on the screen here, I'm showing you a diagram that I think I've shown you in the last video. And you see the cable in question here highlighted in yellow, W914. So I thought, according to the wiring diagram, that to be connected to X517 on the A5 card, on the new card. In reality, it has to bypass that card and stay there. So the diagram on the right is which I believe to be the correct wiring diagram. While I'm at it anyway, this was not the only mistake I found in the Roden and Schwartz documentation. I think I tracked at least 5 other errors in either the CMU or the CRTU documentation, only when it was related to wiring these particular boards. I'll not go through all of them right now, but at the end of the video today, I will show you a couple of overview sheets where I'm going to summarize all my findings and also summarize the errors as I think I found them in that documentation. Now, second point, what went wrong? I bought another unit than I thought I did. So what was going on there? Now, let's take a look at how my unit looked like when it arrived at my home by post. It looked like the unit, or it looked like, this is a picture of it at the top of it. And as you see, there was still wiring in it. This is when I got it out of the envelope, I think already half a year ago or so. There is not a large identification sticker on the top of it that I've seen on other units. I don't think that sticker has been removed recently either, because you can see with the corrosion on the device that's not likely the case. I don't think that the seller took it off for that matter. No, what I think is actually going on is that if these type of modules are already pre-installed in a machine by the time that it leaves the factory, there's no identification stickers on the top. There are some on the bottom. However, when it's later installed into the unit, either by a Roden and Schwartz service center or by the user perhaps itself, then these units have stickers. Now let's take a look at 2 other pictures of units that I got from the internet. In the middle you see a B17 unit, the one that's supposed to go into my device. At the bottom you see the B7. And why do I think that I got a B7 in the end? Well, look closely at the connectors, at the sockets that are present on the devices. You will see that the one in the middle, a couple of sockets are missing. And this is basically because the B17 is a single channel device. It does not have all the same functionality, and I think for that reason it misses some of the sockets over there. So this is when I finally started to understand that my unit was slightly different than what I thought I was installing into the device. Now, does this matter or not? I'm going to look into this now, because that's a bit more of a complicated story. But before doing so, let's quickly look at what are the functional differences of these units. The B17 is for the use in the CMU200 and 300, while the CRTU unit, the B7 unit, is for the CRTU, which is a family of devices, somehow based on the CMU, but certainly not identical. They are designed for other use cases like protocol testing. They're designed for use cases like simulating 2 radio base stations in a telephone network that are doing handover processes, etc. They share quite a bit of the hardware of the CMU, but there are other devices for other use cases. The B7 card in particular can go in the CRTU RU, the radio unit version, the G version, and the S version, perhaps also another version. It's a very complex family of devices there with all the different codes. I'm not going to get into that. Most of the units have an order number, and that can be kind of important to figure out what you got here. The thing is a little bit that there are also a number of other numbers associated with the units, which can make it a little bit confusing. Sometimes they're called stock number, sometimes they're called order number, sometimes they're called part number. Often they don't say at all what this particular number is. These are the numbers here that I've found myself associated with these devices here. And some of the numbers can look really much alike. Look at the two numbers that I got here now highlighted in red. They're almost the same, not exactly the same, and they still seem to refer to different units. I did find out in some cases that some numbers just refer to the bare board, while other numbers refer to the board including the cable set, so the kit as such if you wish. So that could be a difference. More important functional differences, the B17, like I said, is a single channel unit, so it has one TX and one RX path. It's also simply called the IQIF interface. The CRTU B7 unit is a dual channel device, so it has two TX channels and two RX channels, and it's also sold as a dual channel IQIF interface. And this makes sense because I think the CRTU was always sold as a dual channel device with two RX-TX boards in it out of the factory, unlike the CMU. So that's why a dual channel board. Still, I find something peculiar about the B17 being a single channel board. And what is that? That is that the CMU can also have two RX-TX boards in there. That is a possibility, but apparently then the IQ interface doesn't work with all of that. And very strangely, the CMU always has a connector for a second channel IQ interface on the back. There are two of these sub-connectors on the back. That second connector, I think it never gets used in regular configuration because it's not supported by the card. Why that connector is there, don't ask me, I'm not getting the point. How about the outside connectors? Well, for the B17 we got 4 times B and C for IF, and we got 8 times connections, 8 connections on the D sub-connector for IQ in and out. And on the B7 board it's double of that, of both of them. And on top of that, the B7 board also has an additional reference output, a reference-free output that you can bring out to the back of the device. That is physically missing on the B17 board. That connector is not there, but it can be useful. And actually, eventually I did bring it out and I've been measuring on it. And already mentioned these installation wires that have got a wire shrimp on it, which has good information, useful information, because those wires specifically are for the B17 and the B7. So the wiring set is different and what is written on that wiring set. And that can provide us with some clues. Now, why I needed clues there, let's go and look at that. Again, I'm going to look at the wiring diagram. I'm going to blow it up even a little bit more here. Now it's the B17 unit again that's supposed to be in this device. And we see that the outside wiring for IF goes via 4 connectors here. And I've named them. We got an in and output on the transmission part and an in and output on the receive, the analyzer path. Well, all fine. Now, when I took a closer look at the CRTU unit, and actually also about the wires that were pre-installed on my unit, I see it is slightly different. And so what is different? The 2 input wires go somewhere else. As you can see here, the TX in is not at 520, but instead at 519. And the RX in is not at 515, but at 517. So these are differently wired. Now, I think I can be excused for thinking that this meant that these different units had a slightly different wiring to them. Because also I was trying things out and I simply didn't work either the way they were supposed to work, or when I installed it in the device. I don't think that's the case anymore. What seems to be going on, that this wiring is not specific to the board, but the wiring is specific to the host device. And what do I mean by that? If you take a B7 and put it in a CMU instead, actually use different wires. So it seems there's more functionality in there. And in the boards it is, at least the B7 board, it's all wired up, but you connect it depending on the host device that you're putting it into. And after a bit of experimentation, I got it all going in the end in my units. So as to why this is the case, I think I got an idea here, a clue. But let me stress that I'm speculating here. I don't know for sure. But what is my speculation here on what is happening in these units? As a matter of fact, I think that it has two different inputs at the same time present on the device in the B7 unit. And the one input is only used in the CMU context. And that switch is only operated if you put that device physically in the CMU. And the other input is only used in the CRTU mode, I would say. And that switch associated with it is only used when you physically put the device into a CRTU. And I feel a little bit strengthened by my speculation as well when I saw that actually some of the physical characteristics of these inputs are different between the devices as well. So I think actually there's more functionality in the device, and this is something that you really need to know if you want to install this board in the right way into these different type of devices to get the functionality that you want. I mean, the B7 in the end does work in the CMTU. That's what the seller has been telling me, and in that sense, yes, he was right at that. But you really have to figure out what is the exact wiring to get it going properly. In order to document all of that, I've tried to make a table of all the pinout of these two different units in one single sheet here. I'm not going to talk you all the way through it, but should you be interested and want to install them yourself, this could be a useful resource, I assume. Everything, by the way, shaded here in blue. That simply means that it's a BNC connector that goes to the back panel of the device. While all the other things that are not blue are basically internal connections between boards in the device. Now finally, as I admitted, I did not go into the version manager and do the firmware update after board change. I should have done that. I'm going to try to plead myself not guilty anyway. Why did I think that was not necessary? Well, in my device, the new unit didn't show up as a regular type of board that would have something like firmware on it at all. It showed like an empty space when I was looking it up in the setup screen, and I had the impression it was a dumb board, that just the switches were controlled by the CMU, and there might be an APROM to store calibration values, but that's it, no firmware. I'm wrong in that, I know now, the device has firmware. Even now, when I got everything running and I did do the firmware upgrade after board changing, it's still empty, this field. Which is a bit weird, because other people have been so kind to send me pictures of the screen of their CMU, and actually there, the unit does show up. They do have some of the numbers there. There's actually a number I showed earlier that is associated with that car. Why this is different for my unit, I have no idea. Maybe that's because I've been using the CRTU card and the others not. Actually, if I export all the detailed device configuration to a computer file, you can do that by exporting it to a file which is called identity period dot. Then actually this information is there also in my unit. So that number and as well the version or whatever it is, I don't remember how it's called there. But yeah, this I still don't know why my device is not showing exactly the same as other devices is. Now I think that's enough for now. Let's go and do some experimenting. And in the experimenting, basically, I want to quickly look at the confirmation that the unit is properly confirmed. I want to go into the IQ. I want to go first into the IF signals, routing, like the in and the output. That's the one functionality of the device. And then I want to go into the IQ signals in input and output, and it's routing. And then we kind of cover the whole functionality of the device. For my experiments, I'm going to use the CMU for sure. I'm going to use the spectrum analyzer here so we can see some of the IF signals that are outputted by the CMU. I think you're actually seeing already here a IF signal when the unit is in wideband CDMA standard mode. So we see actually a carrier here on the IF output. And to test a little bit more on IQ signals, I will be using here this this fading simulator here, because that's precisely how a fading simulator, or this fading simulator works. It goes into the IQ chain of device, so that's kind of the perfect complement with the CMU of doing some experiments here today. Firstly, let's see if everything properly shows up in terms of the presence of the unit. So here we can go to the setup menu, the options, and now we got software options, but we got hardware options, and we got the IQ interface available. Okay, nice. We can go to info, and here we can find, well, over here the board, and like I said before, strangely enough, this is staying empty, but it still kind of, well, shows up, I guess. A little bit more in detail we will go if we go to the maintenance report, self-testing, because there we can actually have more testing going on. So let's go to maintenance. First the system info. We get a whole list of things. Let's go to the top of that list and we see unit B17 available. Well, okay, so we get all these type the same things. We can do system identity, and that one is actually writing away a file. Here you see it's happening to the C internal drive. And in that file, and I'll show it now on the screen, actually there we find the information that was missing in the setup screen, which says something about the unit. Actually, I found it not so easy to get this file off the machine. Normally you want to get it to the external memory card, and I've been... sorry, that only works when there's a drive in here. Repeat. I spent a lot of time tweaking around with this menu, trying to copy a file from the one thing to the other, couldn't find anything, eventually resorted to the documentation. What you have to do is get yourself an external keyboard, I think something like Alt F4, and then the device runs a number of things, eventually ends up booting in MS-DOS, and then you can copy something to the card. So that was a bit of a thing. But fine, fair enough, we were still in the maintenance menu here. Let's continue to be there. What else would we like to do? We would like to do a IQ self-test. That's kind of obvious. Let's run that. Now it's finished running. And what we see, basically he does some basic testing. He tests the EEPROM that you can access. It's fine. Voltages here. I think there's also some temperature levels. And everything looks fine up to this point. Now, in order to know whether the unit is properly calibrated, and that's maybe the most important thing we got to do now, we should run basically a loop path from the external connectors. So let's go and select that. I'm going to run the external loop path between 1 and 4. I'm going to execute it. And look at that, this is what was wrong the other time, and now it's perfectly fine. We see that all the measurement values in the loop test, and I made a separate video on that where I go in much greater detail on this, are running fine, and it passes the loop test without any problem. Also the loop test from port 2 to port 3 here on the front do well. I already tested that, but I'm not gonna do that right now in the video. So basically, when it comes to the different type of test here in the self-test part, everything behaves as we would expect it to be, apart from the smallest thing that in the that here in the info we don't get to see the exact number of the card, but everything else is just fine. Another thing we can do is overall system self-test. So that's going to be here. I'm going to run it now. And EEPROM is tested. I think that's already what we just did. We're going to get a couple of other things. Let's just wait until we get to the IQ board. IQIF board passed. So everything looks fine in the internal system self-test. Okay, I waited all the way to the end, didn't want to stop it. We also see IF3 self-test passed. All tests passed properly, so the unit seems to be in a fair state. I would like to continue now to do a couple of tests on the IF path, if that is, it is properly working. So to do that, I'll just put the device in RF mode, and we can go to the generator analyzer function. And what I did actually, the new IF connectors on the back of the device, I actually made a loop over here. This is the transmit path on the left, and it's the receive path on the right. And I would like to see if we first actually get to see these signals. So let's first see on the transmit path if we see anything. And right now, I got my spectrum analyzer now connected to the transmit path loop. But right now the unit is not yet in bypass mode. So I go to the control connect. I end up right away here in the IQ menu here. So what I'm going to do here is I'm going to choose, well, we are in bypass mode, but not bypass mode with monitoring. So let me see where it is. Bypass mode with IQ and IF monitoring. So I'm activating that. Yeah, and yeah, so what we're getting to see right away here, we're going to see an IF frequency. We can also see where that frequency is. This is 30.8 something megahertz or so. So this is the IF frequency that is associated with the path here. I'm also going to do it for the receive path. Just in order to do that, let me get the cursor a little bit out of the way. Let me just put this into a memory trace so we can both see them at a time. So trace, memory traces, trace to memory 1. Yeah. So now I've put it into the memory trace, I think. Yeah. So we still see it. So let's see what's happening on the receive path. Yeah, and now we also get to see an IF signal on the receive path. It's a different frequency we can see than we had on the transmit path. This one is actually 10.7 megahertz right now. I think it's unmodulated. Actually, if we look at the specifications of the unit, we will see that the IF path can take different values depending on the mode that you're in, and specifically the type of standard that you are analyzing with the device. Now we basically have been monitoring it, but we don't know yet whether actually we can interrupt the signal well. And to do so, I would like to do that in a type of a mode where I can actually see whether things are successfully being received back. So for that I will be basically using now the one of the standard modes. I'll go to GSM, non-signaling, overview, 8, PKS. Actually, I'm going to go you quickly through the steps how this whole thing works, starting from the clean settings of the device. So let me just reset this whole thing. It's my kind of a useful exercise. So what I'm going to do here. I got the device here at the GSM mode, and I want to look at the IQ constellation plot for 8 phase key shifting. That is actually GSM Edge mode for those that are interested in that. But we're not seeing anything yet, and there's a couple of reasons for that. The first reason here is that that we have to look at the frequencies that are set. So we're now at, by default, because we reset the device at GSM channel 65, equaling 903 megahertz, yeah, on the analyzer. But on the generator, that same channel is 948 megahertz. Why do I see different frequencies even if I'm on the same channel? Well, GSM was a frequency duplexing system, in the sense that the uplink basically was the downlink, I should say, is 45 megahertz higher in the spectrum than the downlink. So normally the terminal receives on one frequency, sends on the other frequency. But now we want the device to talk to itself. So what I'll do, we had 903 here, so I'll fool him into having 903 megahertz here as well. Yeah, that's one thing. Second thing I need to do here is turn the generator on. I did that. Third thing I want to check if input and output are connected. Now I send them to the same connector, so I'm fine there. So I'm almost there, but still getting no constellation plot. Why is that the case? That is actually because it is not yet set to the 8 phase key shifting mode. And in order to do that, we go away from standard GMSK to 8 phase key shifting here. And now I should, yeah, and I get to see it. I get to see a constellation diagram. It's measuring its own signal, 8 PSK. There are a number of things you can do here graphically with it. Actually, you can do this, you see more. This has to do with something with the way that 8 PSK is realized within the GSM standard, because I think they do some pulse shaping and these type of things matter. So we'll just keep it here, and you can do some stuff on ISI removal. But what I'm interested for right now, and I hope you can see it well enough on the video, is the constellation diagram here with its concrete values. But I'm not doing anything with the IQ model yet, right? This is just built into the device, the GSM standard, and this, even having this particular screen, does not require you to have the IQ card. So we're going to go to the IQ card, connect control. You have to go to the second screen. To be very honest with you, I never really understood why we need to have 2 second screens that we're toggling here at the bottom from. I mean, there's enough space left. They could have put IQ here, but well, that's the way they did it. We got a trigger scheme, the IQ scheme. So now I basically want to test whether the insert loops well. So I'm choosing IF in out now for that one. So I got my my constellation back. So I'm on the transmit path. So if I disconnect this here, it should disappear. Yeah, transmit path. Then it's gone. And if I now go to do the same thing on the receive path. Let me get the right one. There we go. And now on the receive path, it disconnects, and it shouldn't matter whether I do something on the transmit path. And by the same means, if I have both of the paths, and let me check out that I got the right one. Yeah, now either of them should disconnect. So the path over here and the path over here. Yeah, so basically the conclusion is that that we can now properly things insert into the intermediate frequency path. And so this was also the whole discussion about the wrong wiring of these connectors. I wanted to make sure that this was acting as it should, and it is. I now want to go and look at the IQ channels, and it's a bit of a similar exercise really, because we're again looking at monitoring and inserting something in the signal path. I'll try to go a little bit quicker now. I'll just go right away to the interruption of the signal path. So again, I've got here at a constellation diagram. I have chosen a diagram here without this removal here. That is a specific thing that has to do with pulse shaping in GSM signal and edge signals. This is going to be easier for our experiment, even though we see double the constellation point. But you'll have to take this from me. So right now we still are in pure bypass mode. So the IQ card is not doing anything. So let's go and change that. Let's go to the IQ card and let's right away go into IQ.io, because then we're testing whether my breakout box is working. And my breakout box now got everything through connected by wires. So if we select this and go out of, yeah, it's still working. And I'm also monitoring right away these signals here on the oscilloscope. And I took the RTB oscilloscope because it's nice. We can see both the time domain and the XY domain at the same time. This is not triggered right now in the sense that we see constellation points, so we're more or less seeing vectors. And we also see the signal is not continuous, we see bursts of signal. Well, again, this is a GSM signal, so we're probably seeing like a time slot here, and if we make it bigger here, yeah, so these are IQ values that we actually see that we have in this particular time slot here. So every, 4 milliseconds or so, we got this this burst of signals with IQ modulation coming by. Okay, great, and we're getting to see here the constellation diagram. Is my IQ interface working? And we're looking here basically at the receive path. Now let's disconnect something in the transmit path. No, and indeed it gets interrupted. We still see something here. This is completely disappearing. I think this is a trigger issue. So I just removed the I thing in the transmit path. If I remove the Q in the transmit path, it also breaks the chain. If I remove I in the receive path, everything disappears. And if I remove I in the Q in the receive path, everything disappears. And so this is basically telling me that all the IQ signals are properly going in and out. Another thing I could do basically is try to see if we attenuate some of these signals and see what's happening. And for this I'll just use a small attenuator here, a 3 dB 50 ohms attenuator, and I'm going to put it in the receive Q channel, and I'll just see what happens. Let me pull it out. Put it back in again. Okay, we get something a bit weird. This signal actually has become half the magnitude on one of the two scales, the Q scale. Let's quickly see if we can verify. And now it's pretty much like a circle, and I can use the cursor here to kind of capture my signal. There we go. Yeah, here. So this is roughly speaking. The cursor is roughly speaking now the side of the signal. So if I put my attenuator in between, yeah, you see one channel is good, the other channel is clearly attenuated. But I'm not seeing that here. And I've been trying to dig into a little bit, trying to understand this. And I think I know the reason now. If we dig into the Roden and Schwartz documentation, we will eventually see that this signal here, the constellation graph, as well as the phase diagrams that we can get from here, both of them are normalized. So it's basically pulling it to -1 and +1 on that dimension, and -1 and +1 on the other dimension. So we're not seeing the real magnitude here of the signal, we're seeing a normalized picture. Again, this is nothing to do with the IQ card that I'm testing here today. This is a constellation plot that's already in the CMU when you got GSM or some of the other standards installed. But this is just worthwhile knowing. There is another particularity going on here, and I hope I can kind of show that to you. And I would like you now to remember that this circle now has a bit of a distortion in one direction. Normally, because it's normalized, he already does that, but apparently then there's still some distortion left. And the distortion is like to the upper left. Do you see that? Now, what I'm going to do right now, and bear with me, I'm going to go to Connect Control, I'm going to analyze, it's now at 900 megahertz, and I'm just going to do as if my transmitter is 1500 megahertz and my generator is 1500 megahertz. And now I got my picture back here at 1500 megahertz, and you see it's distorted to the other direction. And okay, this relates to an issue I've been having last week already. I had the feeling that the I and the Q signal were reversed. I checked this box here for 10 times whether it was properly wired. I checked the CMU pin out, etc., whether that was all properly done, etc. I just couldn't find what was going on. And later I found what the reason for that particular thing is. And actually it's listed in an old version of the manual, I think firmware 3.4, but it has disappeared from more recent manuals, even though the behavior is still there. So what is this behavior I'm kind of referring to? If you operate the unit below approximately 1200 megahertz, the I and the Q channel get swapped. Yes, that's actually what I'm saying. I and Q get swapped. It doesn't warn you for that. I mean, for me there could be a big warning here in the screen. I and Q are swapped. if you even have to do that in the first place. But this is something you want to be aware of. I have no idea exactly why they did it. I'm sure they must have had a good reason to implement it that way. But this is something to be very well aware as a user of this device. Below approximately 1.2 megahertz, you see the exact value in the text. The I and the Q channel get the other way around, and only above 1200 megahertz, I and Q are as they are described in the manual and as I've put it here on my breakout box. Now, as a final experiment, I think I want to use this opportunity to try to put this fading simulator in the IQ loop that we just added to the CMU, because this is really one of the typical test cases that this whole thing was really designed for, that people could do a couple of different testing scenarios on mobile devices, given some fading, multipath fading, noise, impairments of IQ signals, and this unit basically can do that all. It's a very sophisticated unit, not always that easy to use, and very limited only to that functionality. The fact that it's called a baseband signal generator should be taken with a piece of salt, because it cannot generate any signals unless you have a very specific option here installed that is not in this unit, and almost nobody seems to have this option. So it's really a fading simulator and not so much a baseband signal generator, which I wish it was. So again, this thing is now included in the loop. On the CMU, we got the whole loop activated, the IQ loops. It's really going through this, and just to prove it, just look at my constellation diagram, and it disappears when I take it out of the loop, and also here it disappears when I take it out of the loop. So I and Q signals are going through my simulator. Now, what can I kind of show in a limited amount of time in terms of impairments of the signals we can do? Now, we can go here to this unit over here, which is adding noise and impairing the signals. Actually, what we're seeing. So the AWGN, it's a Gaussian noise generator. Actually, it's fairly fascinating the way they create Gaussian noise. And there's a whole part in the user manual that explains what underlying mechanism they use to create good noise. Because good noise is not such an easy thing to make. But that's what it does. So we get to this menu. We can turn it on. We don't see a real effect yet. But now I'm going to affect here the signal to noise ratio. So let's just get my cursor here. So I steps of 1 dB. So I increase the amount of noise, and I hope you can see this at home. We see the noise around the constellation points getting very significant. It might be a bit hard to see on the screen, on the YouTube videos, and I'm reducing the noise, and actually I'm getting a little bit out of range of something, but the noise it disappeared again. So actually we can see here that we can use inserting basically for noise impairments. And I'll try to demonstrate the same thing here basically when we're going to do IQ impairment. So we're going to deliberately do something wrong with the IQ signal. So let's see what we got here. Let's turn this unit on. So we can have an I offset, a Q offset, a gain imbalance, and a quadrature offset. So the angle under which things are happening. So I'm not going to go to the I and the Q offset because we already know here that we're looking at normalized values. But let's try the quadrature offset. It's in degrees. And I'm going to turn this button now. Yeah, so I just returned here the unit to 3 pi over 8 with nothing removed. Then the experiment shows a little bit clearer. So this is now without any impairments being added. So now if I try to add an offset here in degrees, and you have to look quite carefully, I think. I'm going to go like to 10 degrees plus, and you see here there's actually a difference in how the diagrams look like. I'm going to go back here 0 and the other way 10 degrees. And what I also get to see, if I do nothing, basically I have small error vectors and phase errors. And if I make this thing here, I get to, well, almost 10, like 8% of error. It's a very subtle effect, and that's also because this device can only make subtle differences. A more extreme thing would have kind of helped, just for see where things are happening, even in real time, of course, the type of things that this is designed for, and these are already big impairments, 10%. But for the experiments I do, it would be kind of helpful if the differences were bigger here. But anyway, demonstrating here that we can do IQ impairments on this device. Just to give a glimpse of all the sophistication we have here, we can go, for example, fading, where we got all type of fading setups, including MIMO, 4x2 MIMO. We're not going to do that. We're going to go to the simple phasing menu. Right now, for example, we have a fine delay fading type of scenario. I still got some signal coming in here. We can have all types of different fading characteristics, static pass, a pure Doppler, constant phase, Gauss Doppler, Gauss, relay, rise, whatever. We have many of them. We can have like a moving type of propagation. So in a moment I think we're going to see here, and we lost a signal. I'm not going to even try to find. We can have like multiple type of reflection that are being simulated. So yeah, here we're looking at a very sophisticated type of fading patterns that you could do with this device. All right, we're now coming to the end of the video. Now I got it all working. I already will show you a kind of a summary of my findings, as I've been promising before. And I'm not gonna talk all the way through it, but I'm just leaving this as a documentation for those that matter. So I'm first showing here my summary of the wiring of the unit and how you actually have to wire the CRTU unit when you want to put it into a CMU. In my second page of my summary, I want to share with you what I believe to be errors in the Roden and Swartz documentation. So you probably don't want to know about this unless you're actually installing a unit yourself, and then it might be saving you some time. And thirdly, some general observations about installing this unit, most of which, but not all, I think I've been talking already in the video before today. Now, I'm just going to leave these 3 sheets of information for you. That brings me to the end of the video. I must say I'm fairly happy that I got the unit working in the end. It was kind of a headache type of experiment, I must admit, for myself. But end good, all good. I'll be hoping to post maybe 1 or 2 more videos on the CMU, covering some of the functionality that I still want to talk about of the CMU as a generic device. And then I think by then, I think I'm already then at 7 videos or so. I think I pretty much covered what I wanted to cover for the CMU unit, and then we'll be moving on to other interesting stuff again. So thanks for watching, and hope to see you again. And like with everybody else posting on YouTube, please do subscribe to my channel and give a thumbs up if you like it. Okay, see you next time.